So in this video, we're going to talk about the basics of the Sn2 reaction. And then we're going to talk about the basics of E1, E2, as well as Sn1 reaction. Then eventually we have some practice questions on the channel itself where you're able to differentiate. So let's start with the basics. So the Sn2 reaction, right? It's pretty much substitution that's nucleophilic. That's nucleophilic. That's bimolecular. We're going to talk about the idea of bimolecular. Right? It's also second order. So it follows second order kinetics. Or in other words, the rate law that you guys learned in general chemistry. Right? So the N stands for the idea that it's nucleophilic. The 2 stands for that second order kinetics. Right? Second order kinetics or rate law, and the S, no surprisingly, is for substitution. All right. Now we'll say the rate law, we could write it as the rate is equal to K, some constant K, since it's bimolecular. In this case, it's dependent upon the concentration of the alkyl halide as well as your nucleophile. So that's why we say it is bimolecular. Now, one of the big things with Sn2 reactions, we say it is concerted. So it's a concerted reaction, and that just typically means that it happens in one step. It all happens in one step. So it all happens in one step. In other words, what we're saying then is that all bond breaking and bond making happens in one step. Okay? So that's what we mean by the reaction is concerted, or in other words, happen simultaneously. Is another word we could use. Right? Now, for an energy reaction diagram, if you look, we have energy on the y-axis and we have reaction progress essentially on the x-axis. We have some reactants A going to some products B, right? And this is where A goes to B, right? So this is really showing an endothermic reaction for your liking. Now let's look at a quick example, and we have some more examples at the end of the video. But essentially, I have this molecule, and usually again, or reactions are going to happen with alkyl halides. Right? In this case, this is actually a methyl halide, and I have some sort of nucleophile. So the OH is my nucleophile. The OH molecule is my nucleophile. It is charged. It's going to attack the carbon, and then my nucleophile, and then my leaving group, in this case, the iodine, is going to leave. Right? So all the bond making and bond breaking happens in one step. Right? And so if we draw an intermediate state of this, what we're really looking at is a carbon that has 2 hydrogens, well, 3 hydrogens. What we're really saying is that the iodine is leaving while the OH is coming in. Right? And so that's what an intermediate step of this would look like. Now essentially the product of this reaction would be something of this nature. Now, and we get the iodine in solution as a negative charge molecule. Now I want you to take notice of something before we continue. Notice that we had our nucleophile attack from the backside, and it ended up on the backside, right? And notice that our leaving group leave, right? So the nucleophile attacks from the back, it stays on the back. Nucleophile attacks from the front, it stays on the front. Now this is important as when we talk about stereochemistry. All right, so just keep that in mind. Now, if you look at the first molecular reactants, right? So if you look at the methyl halide, there's no stereochemistry. There's no chiral centers, and so we're going to talk about that in another example. Okay. How about the trends in nucleophilicity? So the trends in nucleophilicity, the first one that I want you to take away when we're talking about Sn2 reaction is that charge is actually better. So charge is better than neutral. And we're really talking about that with respect to our nucleophiles. So OH minus is a stronger nucleophile versus H2O. Right? Again, OH, the anion, is charged versus water, which is just neutral. Or in other words, SH minus is a better nucleophile than hydrogen disulfide. Or we can also say that NH2 is a better nucleophile than just pure ammonia. So again, charge is better than no charge. So you must think about this when you're deciding if a reaction is Sn2 versus Sn1, etc., which we're going to cover obviously in the next video. Right. The second one that I want you to keep in mind is that the larger the atom, so the larger the atom, the better the nucleophile. So larger the atom, better the nucleophile. In other words, what I'm saying is that NH3 or ammonia is a better nucleophile than water. Again, this is going back to general chemistry. When you look at the periodic table, you should be able to tell which atom is bigger. In this case, nitrogen is a bigger atom than your oxygen. So the atom size is also important. In other words, we could also say that if we have CH3, CH2, 3 phosphorus, this is better, or it's a better nucleophile essentially than, or CH3, CH2, 2 sulfur. This one you rarely see, but again, it's there. But the idea of phosphorus versus sulfur, again, phosphorus being a bigger atom versus sulfur. The polarizability also takes an effect. So this is the idea of delocalization across the surface area. So this is the idea of delocalization across the surface area. Right now, if you take a look at fluorine, fluorine is about, the size of fluorine is about that, versus iodine. Look at iodine size, right? And so we'll say iodine essentially will be a better leaving group because it's more polar. And so essentially, if you look at an Sn2 reaction versus these with these two, then if we have some sort of molecule where X is an alkyl halide and I have an empty p orbital, then if I look at fluoride minus, okay, it's going to go into the empty p orbital, versus if I do the same reaction with iodine, here's what happens. If I do the same reaction with iodine, I'm looking at a bigger molecule and it's going to attack the empty p orbital. Right? Now, the idea is that iodine in this case, or the bigger nucleophile polarizability in this case it's a nucleophile, it provides a better orbital overlap. So the better the orbital overlap, the better the Sn2 reaction. So that's something that's important. Solvent effects. Let's talk about solvent effects with respect to an Sn2 reaction. So you have to take all these into account, especially when you decide in between an Sn1 reaction and an Sn2 reaction. So Sn2 reactions, we use polar protic solvents. So polar protic solvents. Right? In other words, it has a hydrogen, so something like OH or NH. Something like OH or NH. We use polar protic solvents. Right? Now, here's the thing. This is not the ideal conditions for an Sn2 reaction because it actually reduces the nucleophilicity. Right? So, in other words, we do not use polar protic solvents for Sn2 reactions because essentially it's gonna kind of damage the. Think about it as damaging the nucleophile in a nutshell. Right? So we don't want a solvent that's too good essentially. So we actually do not use polar protic solvents for Sn2 reaction. Rather, what we use are polar aprotic solvents. And these are what actually works best for Sn2 reactions. Right? The idea of polar aprotic solvents. Right? So examples that we use for Sn2 reactions will be, commonly you see acetonitrile. You'll see acetonitrile. You may see acetone as well. You may see DMF, dimethylformamide, formamide. I'm not going to write out the name, but we call this DMF. This is DMF. So common solvents that we use for Sn2 reactions. DMSO, right? So dimethyl sulfoxide. We call this DMSO, dimethyl sulfoxide. And these are the solvents that you'll typically see in organic chemistry that works best for Sn2 reactions. All right. So we need to touch on the leaving group ability before we do a couple examples. So, in other words, the better the leaving group, I want you to think about it. The better the leaving group, the better the Sn2 reaction. Better the Sn2 reaction. Right? And that should make sense. Now, remember we spoke about size. So, in other words, we're saying that fluorine is in other words, what we're saying, chlorine is a better leaving group than fluorine, and bromine is a better leaving group than chlorine, and iodine is a better leaving group than bromine. Right? So in other words, on this scale, iodine is the best, fluorine is the worst. In other words, and actually, we don't even use fluorine in organic chemistry as a leaving group because it's so small. So those are some of the leaving groups that you'll see with Sn2 reactions. Quick note, other leaving groups that you may see. You may see something like this, where R is just any group. So you may see a leaving group like that, or its resonance structure. You may see that as a leaving group. Obviously, you may see water as a leaving group as well. So water is common. You can see water as a leaving group as well. It's mostly common in Sn1, but it's still common. It's still relevant in Sn2 reactions. And this is water as a leaving group. Quick effect before we jump to our examples. The last thing you need to know for Sn2 reaction is the substrate effects, or in other words, the alkyl halide effects. So we actually say a methyl halide is better than a primary alkyl halide, which is better than a secondary alkyl halide, and way better than a tertiary alkyl halide. And I need you to pay attention to what I'm about to say. You never want to do Sn2 chemistry, so never do Sn2 chemistry on a tertiary alkyl halide. It just doesn't happen. If you put that on your exam, you're going to get that wrong. All right, so if you see a tertiary alkyl halide, that means a carbon with no hydrogens. You should not be thinking about Sn2 reactions. I do not care what the conditions are. Now, if the professor specifically tells you that I want you to do an Sn2 reaction, then obviously do it, but you really never see that. Right? So never do Sn2 chemistry on a tertiary alkyl halide. Now, again, just to repeat and draw out the structure, here's the methyl alkyl halide, where X is the alkyl halide. We have a primary alkyl halide, and we have a tertiary alkyl halide. I'm sorry, a secondary alkyl halide with just one hydrogen, versus a tertiary, which really contains no hydrogens. Right? So this is a tertiary, secondary, primary, and this is your methyl. Now for Sn2 chemistry, really, even though I said that the methyl is better than a primary, really in organic chemistry, we really use the primary as the best one, right? So even though you see methyl chemistry, we really use primary alkyl halides as our best substrate. Right. So the last thing that we need to talk about is the stereochemical effects. Or stereochemical outcome of the Sn2 reaction. Right? Now, I want you to take close attention to this. If you need to show stereochemistry, or stereochemistry is shown in the problem, you need to show stereochemistry as a product. Now, Sn2 reactions, if you originally have a chiral center that's R, it's going to go to S. Or if you originally had a chiral center that's S, it's going to go to R. Now, all these on this side will be my reactant, and this side will be my product. So all I'm saying is that the chiral center of interest changes when you do the reaction. Right? So let's do an example. Let's say we have this molecule. Now, if you notice, I'm looking at a chiral center, right? My carbon has 4 different substituents bonded to it. If I take OH as a nucleophile, it comes in, attacks the carbon, displaces the bromine simultaneously in one step. As a result, notice that my OH is attacking from behind, so my OH will stay behind. Nothing moves, CH2, CH3. My bromine leaves. I still have my CH3, and I have my hydrogen. Now, I'm not going to go through this, but if you do your rules, you'll actually see that the chiral configuration center for this is actually an S, where this is an R, where the product is an R. Right? So that's what I mean, that if stereochemistry is shown, you need to know that chiral centers switch. And you must keep that in mind when we're dealing with stereochemistry with Sn2 reactions. Another example. Right. Now, let's take into account, right? So let's take into account the idea of this molecule, and we're using OH as the nucleophile. Well, if you notice that this carbon, we're dealing with a primary alkyl halide, 2 hydrogens, it's going to come in, attack the bromine, attack the carbon that contains the bromine. My leaving group gets displaced, and so essentially, this is my product. Now notice that no stereochemistry is shown here because we're not dealing with a chiral center, right? Let's look at one more example that looks at stereochemistry. I take this molecule, there's my bromine, there's my CH3. I take this molecule and react it with SH minus. Well, I'm going to attack the carbon that contains the bromine, the leaving group. Now in this case, if you look at it, the bromine is really going down, so I'm attacking from above. Essentially, the bromine leaves in one step, and so the product should be the SH now coming at the top, and again, nothing changes with my CH3, and I get the bromine in solution. So that is kind of the gist of Sn2 reactions.